Hi, this is a video about the gas laws. So there's Boyle's Law, Charles' Law, Gay-Lussac's Law, and then eventually we combine them into something we call the combined gas law. So Boyle's Law is the relationship between pressure and volume. So if pressure were to increase, then the volume would decrease for a gas. So this would be like if you had a syringe. You can see in the pictures, as we push down with more force, more pressure, then this volume keeps getting smaller. And then if you were to graph it, it would be an inverse relationship. So as one variable increases, the other variable decreases. So the math, by the way, our lungs work this way. The diaphragm, this will lower, which causes the volume to increase and the pressure to decrease when we inhale. And then, if you remember the gas laws, the one with the marshmallow was the station that was Boyle's Law. So you have your gas particles, whether those were in the marshmallow or not. When you lifted, your number of particles stays constant, the temperature stays constant, but the volume increases. So this one is showing that as pressure goes down, the volume went up. So we can do calculations with Boyle's Law, and we do use the equation P1 V1 equals P2 V2. So the ones are the beginning conditions, and then the twos are what it changes to. The volumes are normally in liters or milliliters. If you do have two values, they have to be in the same unit. Similarly, the pressures have to be in the same unit. So when we read this question, the diver blows a 0.75 liter bubble when they are 10 meters underwater. And so that would be our original volume. And then they rise to the surface and the pressure changes. So the initial pressure is 2.25 atm. And then when they get to the surface, the new pressure is 1.03 atm. And then we want to know what would the volume of that bubble be. So then we can just substitute into the equation. And we would have 2.25 atm times 0.75 liter, and then 1.03 atm times V2. So V2 is my X. So I can stop at this point, or just calculate it if I want, or you can show your work. This is what we're doing, the algebra. So you can see the ATMs cancel and you end up with liters. And then in terms of the answer, let's do it. So you should think about the pressure went down, so the volume should go up. So your answer should be bigger than 0.75, and it is. It is 1.6 liters. So that is your answer. Now I want to talk about temperature. Absolute zero is 0 Kelvin, and at that temperature, all motion stops. There's nothing below that, so there's no negative Kelvin degrees. And when we do our calculations with gas laws and temperature, we do have to convert those temperatures into Kelvin, so that we don't end up with like negative volumes and things like that. So the equation that we're going to use, and it is on our pink sheet, is we take the Celsius temperature and then we add 273 to convert to Kelvin. So Charles' law is the first law now, we did Boyle's. This law does have temperature in it. So this law is just stating that, if you were to increase temperature, the volume will increase. So these are directly proportional. And this is the equation. And then again, here's kind of a picture. So as I heat, remember how we draw those arrows on our particles longer to show that they're moving faster. So as temperature increases, kinetic energy increases. And if allowed, then the volume will increase. It won't if you have like a rigid container, and we'll talk about that soon too. So if you were to graph the temperature and the volume, it's a direct relationship. So it is just a linear graph. So Charles' law example. So we have a helium balloon and it has a volume. So these are my beginning values of 2.32 liters, and my temperature in my car is 40. And then if the car was parked on a hot day and the temperature increases, so that would be my new temperature to 75, what would that new volume be of my balloon, assuming that it doesn't explode? So before we can really do the problem, the V1 over T1, V2 over T2, we do have to convert these temperatures. So T1 is going to equal Celsius plus 273. So that would be 313 Kelvin. And then T2 is 75 plus 273. And you don't have to show your work for these if you don't want to. I'm just doing it because I am teaching it. So once you have those then in Kelvin, they are, these are your variables. So we can then plug in. So 2.32 liters over 313 Kelvin equals V2 over 348 Kelvin. And then you just want to do the algebra. Personally, I just crisscross, or I cross multiply. And so then I get V2 times 313 Kelvin equals 2.32 liters times 348 Kelvin. And then I can see that I would need to divide both sides by 313. If you can do all of that in your head, then the only thing you would show is this, and then your answer. But also make sure you show your equation. So when I do this, the math, I get 2 point, we're going to want 3 sig figs, so 2.58 liters. Then you want to ask yourself, does that make sense? The volume increased and the temperature increased, so that does make sense. So Gay-Lussac's law is also involves temperature, but now this would be like if you had a rigid container. So in terms of the stations that we did, the gas law stations, the Charles law station was when we had the water bottle, and we had it in cold water or hot. Let's say we started with hot here. Then once we put it into the cooler water, it kind of collapsed. And again, that was because we purposely used a water bottle that's the volume can change. Some water bottles are a little bit more rigid, but notice that my moles of gas are constant, but my temperature, I'm showing that temperature was lower with those smaller arrows. So Gay-Lussac, this example would have been the steak bottle, where, we had with the dime, the bottle itself, volume couldn't change. So we had it in the cold water. And before the dime moves, your moles of gas are constant. And then we heated it up with our hands, and again, that volume of that bottle doesn't change, and the number of moles of gas doesn't change until it finally, released that pressure. So in that bottle, you have pressure pushing out. I'm showing that with the red arrows. But when you heated it, that pressure increased and eventually caused the dime to flip up. So the equation is here. And then we also, so we know when we see that kind of a relationship with that these two variables are directly proportional. So as temperature increases, pressure increases. So if I were to, here's another picture of this and a graph. So my graph is going to look similar to Charles' law because they're directly proportional. And then my picture is just showing that these particles are moving faster. They have more kinetic energy because they are hotter. And then that increases the pressure from what it started at. So if we do a problem here, so if we are calculating the pressure of oxygen gas that's in a rigid container, and the pressure is, so this is our beginning pressure, 5.0 atm. At temperature, my beginning temperature is 25 Celsius. And then we somehow, we move the container up to a camp that's high up on Mount Everest. And it's going to be cooler up there, so -10 degrees. So we want to know then what's the new pressure in that canister. So again, you do have to do those temperature conversions. So T1 would equal 25 plus 273. And then T2 would equal -10 plus 273. So this is going to be 298 Kelvin. And this one will be 263 Kelvin. So then I'm ready to plug into my equation. Whoops, P1 over T1 equals P2 over T2. So then I can plug in my 5 atmospheres over 298 Kelvin equals P2 is my X over 263 Kelvin. So again, you can just stop at that point and solve, or you can show your work. We cross multiply. So it's 5 atm times 263 equals P2 times 298 Kelvin. And then, I'm kind of over here. Then I would divide both sides by 298 Kelvin. So those cancel. So P2 equals 5 times 263 divided by 298, which is 4.41 atm. So my temperature went down, so my pressure should go down, and it did. It was at 5 and it dropped down to 4.41. So the combined gas law is what is on your pink sheet, P1V1, and we actually have mole in there. We're not really going to see any problems with moles, so essentially we will, when we start to deal with the ideal gas law, but each law is in here. So it's not always just two variables. Sometimes more variables are changing. So in this law, like this top part is Boyle's law. And this is Charles. And then lastly, this is Gay-Lussac. And then there is one law we didn't cover, which is Avogadro's law, which would be the volume in the moles. So as the moles increase, the volume increases. But we are going to focus on just pressure, volume, and temp. So here's an example of a problem. So we have a gas with a pressure of 110 kilopascals, temperature is 30. So I'm going to add 273 right away so I don't forget and get 303 Kelvin. And the initial volume is 2 liters. And then the temperature is increased to 80. So 80 plus 273. So that's 353 Kelvin. And the pressure is increased to 440 kilopascals. What is the new volume? So just to beware, like those two pressures have to be in the same unit. If they're not, just convert one of them into the other so that they're in the same unit. So then when we do this, we're just going to sub in. So 110 kilopascals times 2 liters over 303 Kelvin, and then 440 kilopascals times V2, which is my X, over T2, which is 353 Kelvin. And you can stop there and solve, or if you want to show your work, cross multiply. When I cross multiply, I would get V2 times 303 Kelvin and times 440, kilopascals, and that equals 110 times 2 times 353 Kelvin. And then I would isolate my variable by dividing both sides by 303 and 440. So you can see that cancels. When you do keep the units in there, you can see that the kilopascals cancel, the Kelvin cancel, and you're left with liter, which is kind of nice to know that you most likely did it correctly. And I'm going to put this in my calculator. And with originally my numbers have 2 sig figs as my lowest. So with 2 sig figs, my answer would be 0.58 liter. So that is it.